morning and welcome to the 2013 annual technical review and meeting of M-OSRP. We usually start the meeting by going around the room and people just say who they are and where they come from. B Weglein from the University of Houston.
South Being from PS. John from PP.
Jackson Peter, Petrobras.
Petrelo PP.
Cristian Rivera, total.
Kevin Costa, Western Jacob.
Tongbo Lee from PGS.
Sam Galvin from Chevron.
Dave McKidd in Canada.
Maria Zhang from Chemical Physics.
Shi Wong from University of Houston.
Tom, I'm from University of Houston.
Shabendi, University of Houston.
From your batch.
Lin Tang from University of Houston.
Wilbert Herrera from the University of Houston.
Jan Edel from University of Houston.
Wang Yang from UH. Chen Lin from University of Houston.
Xiang Fu from UH.
Tom McClure from IBM.
Jim Mahan, U of H.
Jin Wu from UH.
Jin Yang from U of A.
Mark Smith from U of H.
Yafei Wu from Anadarko.
Ernesto Pesa from Anadarko.
Alex Wang from Spectrum.
Scott Morton from Hess.
Thomas Collison from Hess.
Paul Terry from PGS.
Welcome. So we wanted to express our appreciation and gratitude to our sponsors. We have a growing number of sponsors, and several are here today. Okay, so we go through this boilerplate kind of discussion every time we meet about what we're about, so that we remind ourselves of what the big picture is that motivates and drives this consortium. We're set up to address seismic EMP challenges. So the first question is, how do you know there are challenges? If you want to know that whether there are challenges, you can look at the drilling success rate in the deep water Gulf of Mexico, and that will quickly convince you that there are certain open issues that are in any procedure that we have ever used, including the procedures that we have in this group. There are issues. So what resides behind the challenges are that methods make assumptions. Every method makes assumptions. Every method that we will ever think of or pursue will make assumptions. And when those assumptions are satisfied, those methods are effective. And when they're not satisfied, those methods have difficulty. And the end of that is either drilling dry holes or less than optimal development zone. What types of assumptions? It's convenient to categorize assumptions by acquisition assumptions, compute power assumptions, and innate algorithmic assumptions and requirements. And acquisition means, did you collect the data that the method requires? Compute power, do you have the compute power to allow a turnaround time that's meaningful and relevant? Innate algorithmic assumptions are the kind of assumptions that we focus on. What are the assumptions within the algorithm that are either not satisfied or the requirements of the algorithm are not satisfied? So there's two ways to deal with an assumption breakdown. One is to remove the breakdown by satisfying the assumption. The other is avoid the assumption violation by deriving a method that doesn't make the assumption. One or another of these approaches is reasonable, and we adopt for different types of problems. So for example, collecting data. Wave theory methods need the data. We don't know a method that can achieve wave theory methods without collecting data. We collect it, extrapolate it, interpolate it. There was a Geophysical Society of Houston article that said April 1st article that said Weglein claims to do depth imaging without data. It was a joke, but the number of our sponsors increased, so I was happy to hear that. I thought it was very funny. They actually showed one trace with one event, and then a 3D full depth section. And they said, Weglein said he really didn't need that event, it was just the first step towards it. And anyone who disagreed with him is just conservative, old thinking, you know. So that was very funny. Okay, so M-OSRP takes ownership and responsibility for the entire processing chain. In other words, if there's some pre-processing method that's required for one of our processing methods to reach their potential, we don't take the attitude that that's someone else's problem. That's our problem. And so that's what that means. And you'll see examples of that. So this is a view of the way M-OSRP, mainstream M-OSRP, views things, that pre-processing, acquisition advances to a sensor over the cable have provided a huge opportunity and, for both pre-processing and all subsequent. That's a development that I never thought would come as fast and has tremendous implications on all of our objectives. So we view pre-processing things like separating a reference wave from the scattered wave, separate the wave that didn't deal with the Earth from the wave that has experienced the Earth. The wave that hasn't experienced the Earth also carries information. We don't want to just separate it, we want to use it. And then we want to deghost data. We need to source and receive the deghost, and we need to source and receive the deghost well. We know that there's an industry uptick on deghosting due to FWI efforts, low frequency interest. Okay? We're happy if what we do helps that, but one of our motivators is that all of our methods, all the inverse scattering series methods, have a nonlinear interest in deghosted data. And if you don't provide that effectively, every single step along the chain, free surface multiple, internal multiple, and so on, will be injured. There's a nonlinear dependence on that. So you'll see a lot of effort in that kind of, and for us, Green's theorem provides a framework for that kind of pre-processing. It also provides a framework for understanding migration data. It's the basic method that says Green's theorem in terms of wave field prediction. In other words, we see Green's theorem as having two major thrusts for us. One is wave field separation. It's kind of separate the reference from the scattered wave, and deghosting, we view that as wave field separation. Separate, you have the measurements separate at the receiver, the waves that arrive at the receiver moving up or moving down. Wave field separation, deghosting. There's a wave field prediction is, for us, a key step in traditional migration. You predict what a receiver and source would be at depth, and you apply an imaging condition. Green's theorem is the fundamental cornerstone of math physics that says, what do you require on a surface, wave field measurements on a surface, to predict the wave in the medium? So when you come to some new kind of prediction, in other words, where did you ever hear that surface measurements are adequate? Where did that come from? You have to start with some theorem that tells you that the surface is part of a closed surface, okay? And you have to deal with those other surfaces, or you're on shaky ground, always assuming that what's on top is enough, and especially when you come to two-way propagation. And Green's theorem, thanks to George Green, 1826, provides all of that. Okay, so that's the our main the mainstream processing chain in recent years have accepted free surface and internal multiples. I would say more than accepted. They use, they publicize, they market methods that have their origin either on history or from within this group for free surface and internal multiples. It is no longer hugely controversial that you, in principle, can remove all multiples without subsurface information. That was a big controversy, as many of you remember. There would be, every time a comment like that was made, people would get up at the SEG and there'd be a whole tussle. Yes? That's no longer a controversy. That's a tremendous step. In conventional, meaning mainstream processing, however, everything beyond multiple removal, depth imaging, AVO, and all the rest, still depends on having subsurface information. And we've had something to say about what might be possible and have put our toe into that arena from the inverse scattering point of view. And we'll have some words to say about that. So we're looking for a consistent and aligned link of processes. We don't want a step early in the processing chain to make an assumption that is in conflict with a method it's meant to serve further on the chain. If you assume a 1D Earth for pre-processing and you get some result, and then you put that into a method that is assuming a multi-D Earth, perhaps the pre-processing doesn't match the processing assumption. So we want to avoid that kind of situation. The M-OSRP processing chain has, if you want to say, one key element, one key, it is from beginning to end, do everything without subsurface information, everything, pre-processing, processing, without needing any subsurface information. That's a high order, and it's moved into multiples, of course, where that was controversial, not controversial anymore. Depth imaging without velocity is controversial, to be kind, okay? And we can accept that. Okay? We can accept that. And so the thing that has changed in the last several years about our activity is the following. Back in 2011, when we started M-OSRP, I was sick of multiples. They were very good to us, but I was sick of looking at them and trying to get rid of them. And we felt that they were sort of mature, and we ought to be an academic fundamental research effort. Go look at a tough problem, depth imaging without the velocity. The sponsor said that that's all very well and good, but we could actually use some of those multiple attenuation codes. So why don't you do that? I know it doesn't thrill you, but just do it, okay? Provide some value along the way. And we did, but we thought it was paying the rent. We didn't think it was a fundamental issue of, those fundamental issues had been addressed. Well, in the last few years, it turns out that what we and Delft and others did to address issues when 25 years ago industry moved to deep water are no longer adequate. There are new challenges in multiple removal for onshore, for complex salt layering, for unconventional plays that are beyond everything we have delivered and beyond everything we know how to deliver. That makes it a fundamental issue. So multiple removal has moved back from something we would want to hear about to center stage in terms of a research project, and you'll see our efforts to get into that. So let me give you, rather than make it a big mystery. For example, in the days of 10, 15 years ago, if you ask people what's multiple removal about, they would say there's a prediction and subtraction. And all our errors and sins we make in the prediction, that the adaptive subtraction will fix it up. There's a lot of confidence in energy minimization, adaptive subtraction. Eric for sure, Hoops-Bergout introduced it, Cavallo, and I published on that same energy minimization adaptive. And it was useful. If you had some isolated multiple, and here is its prediction, and nobody else was in the neighborhood, it's a very effective method. And if you didn't do that, you didn't get the multiple out, because you left things out. You didn't, in the Delft case, they left out the obliquity factor, the sloppiness, and in our own experience with getting ghosts out. If you start to compromise things that affect amplitude and phase, you're expecting something to fix it at the end. People who don't like that idea call it a kludge. People who like it call it adaptive. Okay? I call it adaptive. There's always a need for adaptive. There's always a need for a dial to fix up what you left out, and there will always be what we left out. And the idea is, make sure the criteria for that dial is as intelligent and fits the purpose today as is possible, and that you don't overburden it. So what's the problem? If you talk to people from Saudi Aramco, they'll tell you the number one problem is every single primary they seem to have has a multiple on top of it. Interfering. In other words, they're not isolated. So the whole criteria of energy minimization adaptive, if you have an interfering primary and multiple, you could have a destructive interference between the primary and the multiple. When you take the multiple out, the energy goes up, not down. The whole criteria, forget about how you apply it, is the criteria fails. Okay? So we need a replacement. We need a replacement for the adaptive, number one. Number two, we need to reduce, while we're looking for a replacement and developing replacements for energy minimization, we need to reduce the burden on the adaptive. Every single thing that we can do algorithmically to produce the amplitude, phase, and shape of that multiple needs to come in. So you surgically remove the multiple. All the pre-processing steps that are assumed by the algorithm that have done their job have to be heightened attention. So that theme goes throughout this meeting, okay? That shift in emphasis. So, for example, how do you get the wavelet, how do you get the reference wave out on land? How do you get the ground roll out? In other words, if multiple removal onshore is so prioritized, we have all these methods that have shown value, and you'll see examples with seam data and field data of deghosting and so on for marine. Well, if one of the biggest issues is onshore, how are you going to do that onshore? Where's the theory for that? So you'll see progress on that. So I'm giving you sort of the big picture. None of our processing chain elements has been dropped. It's just in response to a current need that we feel we're well suited to address. We know about the inverse series. We know how to mine its potential. We know how to improve. No, we don't know how to improve the amplitude, but we know the series does. And you'll see entry into that by several speakers. You know, in other words, the internal multiple algorithm today, to D'Araujo and company, is an attenuator. That's the most effective internal multiple code developed and delivered in the world today. It's an attenuator. It predicts the exact time of every first order internal multiple, no matter what the history. It could be P, P, S, P. It gets the time precise. The amplitude is approximate of the result. In times past, that was fine. You have an isolate. It isn't fine anymore. Do we know the series has the capability to make it fine, make it the amplitude? Not attenuate, eliminate? Yes. Have we captured it entirely in some algorithm? The answer is no. Will you see progress towards that here? The answer is yes. Okay, that's what I mean by a fundamental issue. Fundamental issue is you can't write the equation down. Okay. And we need it. We need it as the petroleum industry for priority shifts in portfolios. We hear this from people from shale gas and shale oil. They're suffering multiple problems. Okay, so that's a long-winded. So this is the agenda. The agenda takes us through the processing chain. So I'm not going to go through that now, every single thing of the agenda, otherwise it will take 2 days. So, but as we get to topics, I'll say a few introductory words on major topics within the chain. Okay? So you see we go from pre-processing to multiples, and then what's up with ISS imaging, a new method for RTM, a wave theory for RTM, and we'll define what we mean by that, and you'll see some steps towards that goal. That RTM asymptotic and wave theory method is our traditional. So, it assumes that you have information about the subsurface, which is what we do in the RTM today. It's just proposing an alternative that could have value within traditional thinking, and when it could have value. And there will be examples shown of very impressive examples. Okay, so in terms of every day there's a lunch, there's breakfast outside. Tonight there's no, the group will need to further prepare, but there's no meeting dinner. Tomorrow night there's a dinner. And then traditionally the sponsors meet after the meeting's over. Scott Moon is the chair of the board, and to talk amongst yourselves and then to talk to me. So we said that Green's theorem is a cornerstone for these pre-processing methods. So we're going to say a few words. So I mentioned already, there are two different, very different types of applications that we derive from Green's theorem for us. Green's theorem has many, many applications outside of what we're interested in. But for us, as I said, there are two. And this morning, we're only going to focus on one, wave field separation. With Green's theorem being applied to wave field prediction for RTM, I'll cover that right before we talk about RTM, rather than cover that all now. So let's start. The Green's theorem is not an acoustic theory. It's a theory which is much, very general. And in fact, when we write it in terms of acoustic looking forms, it's already more general than the form implies. But just to get specific, here's a variable velocity, C of R, single frequency acoustic equation with some localized source and RS and a frequency, is there a pointer? No pointer. And no whiteboard.
We're going to set up the whiteboard at the break.
Okay, thank you. Thanks. Good night. Okay, so this is the velocity, and as we often do, we'll take the actual velocity configuration and describe it in terms of a reference velocity and a perturbation, where and then we introduce k is omega over c0. We get a form like this. We put this reference differential operator on one side and everything else on the other side, and we call everything else on the other side source. And the sources have two types in this simple example. Sources can be, here we would call this an active source. It's where the energy starts, and this is a passive source, a source of the scattering wave. But for the purposes of this morning, it's rho. In fact, you could, if you were worried, how come this is an acoustic theory, it's an elastic earth, you can write, and we'll show that tomorrow, for a different purpose. You can write the elastic equations, a couple of P and S equations, in a form where and then you take these couple of equations for P and S in, let's say, some heterogeneous, elastic, isotropic medium, and recast it as a single equation for phi with a complicated right-hand side. Okay? Where you have all converted wave potentials and so on. So this form is, with a rho here, is broader than the acoustic simple steps we took to reach it. It covers having an elastic earth with a water speed reference. Okay, so with that form, we'll introduce a Green's function, in other words, an idealized solution to that reference medium. So this is a description of the world. In other words, this is what I would call a reference medium source description of the world. The world is broken up into a reference medium and sources, rows, that together give you the actual world. Okay? And so, whatever that row is, and we gave an illustration with two terms, but it could be much worse. But given this G0, if you take a causal solution of this, then the causal solution to the equation on the previous page, this equation is just by linear superposition, a superposition of the elementary solution, the local solution, due to a source at R prime and a field point at R, with a weight at R prime, wherever the source is at R prime. Okay? That's all it is. So that solution is valid for any point R in the world, and assumes that all the sources in the world have been included. And it also assumes that all the sources are in a place that you can integrate. They can't be an infinity or something. Okay? That has to be integrable. Okay? But within that, it's very general. There's a second form, so that's statement number one. That is just linear superposition. There's another form from Green's, called Green's second identity, which its ancestry is Isaac Newton and Leibniz, the ancestry. In other words, that you have an integral, f of x dx from a to b is phi of b minus phi of a. That fundamental theorem of the integral calculus says you have an interval of x, you integrate something over it, and it's replaced by something else at the endpoints. Okay? Something else, the antiderivative. That leads to the divergence theorem, leads to Gauss's theorem. Surface and volume comes all from Isaac Newton kind of thinking. So P and G0 here are anything. But for our purposes here, one will be the actual wave field, and G0 will be the impulse response in that reference medium. When you substitute the differential equations for P and G0, you get the following expression. You get that for a point R in the volume, in other words, you get an expression where there's an integral over P of R prime omega delta R minus R prime, and it asks, is R in the volume or not? If R is out of the volume, you get a 0. In other words, this plus this is 0 for R out. For R in, this plus this is P. Okay? For P and G0 satisfying their differential equations. So this equation has tremendous richness. It leads to wave field separation methods. It leads to wave field prediction from the same equation. This one equation leads to deghosting, leads to RTM, all kinds of things that one-way migration results. So we're focusing on wave field separation. So what we're going to do is we're going to take that expression where we integrated rho G0 plus over all space, and we got an all, a minute ago this was an integral over all space of rho G0 plus, and we're going to break the integral over all space into an integral over a volume plus an integral over the whole world except that volume. Yes? So this plus this is P for any R. This is a very important step. These two steps, it will explain all these deghosting theorems that have come from Green's theorem, for example. So what you do is you look at this expression. It says P for R in the volume only is this plus this. This equation is for any R, in the volume or out of the volume. You get this plus this. But in the volume, this is an expression for P. So therefore, for R in the volume, this second term must be this second term. Okay? That's the key. This is not a new theorem for us. In page 100 of Born and Wolf, it's there. In chapter 7 of M-OSRP, it's there. Old classic math physics. We're just exploiting it for seismic purposes. So you get this statement that the surface integral is the contribution for a point R in the volume gives you the effect of sources outside the volume on the field in the volume. So, let me summarize. If you want the wave field everywhere in the world, you need to know the sources everywhere. That's it. If you want the wave field in some volume of the world, then you need to know the sources in that volume, and then there's a surface integral that gives you the contribution due to sources outside on the field inside. That's basically the story. So that's what you're seeing here. This surface integral gives you the contribution due to rho's outside the volume, on the field inside the volume. That leads to all kinds of consequences. Okay? That's that thought. So one thought is how to get, okay, so first let me be clear. This P that's in this formula is the entire wave field. It's not part of the wave field. It is a surface integral with the entire wave field there, or in seismic terms, on your cable. It needs the field and the derivative, the normal derivative. Okay? What it does is it breaks the field up. It gives you a portion of the wave field. You can see already separation coming, yes? It gives you the portion. When you evaluate this inside the volume, it gives you the portion of the wave field due to sources outside. Due to sources outside. It takes a wave field due to all sources, does an integral, and filters out the wave field. When you evaluate inside the volume, it eliminates, it filters out the portion of the wave field due to sources in the volume. It only gives you the contribution due to sources outside. That's why Born and Wolf on page 100 call that the extinction theorem. It extinguishes the field due to the sources inside. It gives you the contribution outside. That's most of us I say it in a positive way. They say it gives you the contribution due to sources outside. Okay? Born and Wolf say it extinguishes the field due to the sources inside. They're the same thing. So we're going to show now two applications of that, two different wave field separation applications, and then show progress on the deghosting part. Okay? Progress in many different, for many different issues, and including what type of deghosting is best suited for 3D, what type of deghosting is best suited for ocean bottom, for land, for, yes. What are sampling issues on which type of ghosting you will choose? Okay, so please remember, this thing is talking about there are sources outside and there are sources inside. There'll be a point when we get to land where we want the source on the boundary. We have the measurement surface, and the fiber size is not in the air, it's on the boundary. What's this gonna say? You'll see what we've developed to deal with that. That's what I mean by something new. The world's been broken up into sources in and sources out. What if it's on the surface? Okay. So that's addressable. But it's only addressable with one type of application of this. It depends on the domain that you apply this, whether it'll allow that to happen. So that's interesting. In other words, if you're in X omega versus KX omega, one will allow that to happen and one will not. So there's a preferred domain to apply wave field separation if you're on land. And you'll see why in detail. So, okay. But right now, we're not going to worry about that on the boundary business. We're just going to say, consider a world where the reference is air or vacuum and water. That's the reference medium. And then there are sources, two sources sitting on top of that reference. There's one source is the air guns and the other is the earth. So the reference is air and water, and you put two sources, and now you have everything. That's a choice. You break up, your only commitment is that when you finish background and sources, that adds up to everything. In a minute for deghosting, that will not be the breakup. This is a specific breakup, where it's air and water is the background. In a minute, we'll make water everywhere as the background, and then there's three sources. One that makes water into air guns, and earth. That's the deghosting one. Again, the only commitment is that background plus what you superimpose adds up to reality. How you break it up is your convenience, your application. So this one is for getting the reference wave and the scattered wave separated. So, and this goes back to some work with Seacrest in 1990 at that time. So, this is the reference wave now. In other words, once you define the reference medium, then the reference medium defines the reference wave. If the reference medium is a free surface and water, that's the reference wave. If the reference medium is water everywhere, the reference wave is just direct propagating. So the reference wave has no meaning until you say what the reference medium is. Okay? So for this reference medium, that's the reference wave field. Then that integral on top, with that G0, the one we just had a minute ago, evaluated for R in here, if you close this way, as you see this surface, and that cable is just, and you evaluate a point here, it gives you the, what do you evaluate? You evaluate this integral on this surface, and by Sommerfeld, this will vanish, vanishingly small contribution as this gets large. P causal. Okay? So you end up with a contribution here. What this gives you is, it gives you the contribution to the total field due to the sources outside. The sources outside in that reference medium. So there's only one source outside, the air guns. The reference is vacuum and water, and there's two sources in this problem, air guns and earth. One is under the cable, and one is above the cable. So when you say due to the source outside, it's due to the air guns. And so with that, you get that if you call the row air guns with G0 plus, where this G0 plus is this, for reasons you just mentioned, you get the reference wave. You get the wave that the air gun array, let's say, what would it predict at a point below the cable? In other words, in the reference medium, that's what it gives you. So that was a way back in the day to get the wavelet we were interested in. And this gives you more than a wavelet, it gives you the radiation pattern. But if you have if P0, in other words, if the air guns are an air gun, and that air gun is isotropic, then it's a single A omega, like that. And then that formula reduces to this. And for every point in the subsurface, you'll get an estimate of A of omega. So this is a robust method to get the wavelet. This was published in 1990. There was no acquisition for it. Once in a while there'd be an over-under cable, but it wasn't normal. Now it's normal. You have service companies getting that kind of measurement. Yes, P and normal derivative in different varieties. And we'll talk about those different varieties and specifically what in our view each adds, and then a proposal to improve in detail applying things like this to their acquisition issues, okay? So we're going to get very personal in this kind of detail. This is just theory right now, okay? So now we're talking about ghosts. Just for those who haven't heard of ghosts, a source ghost is an event which began its history leaving the source moving towards the free surface. And a receiver ghost is an event which, when it's recorded, is moving down at the receiver. Okay? That's what it is. We want those removed for reasons I don't have to go into. The notches, the interference, those notches can be destructive to the actual character of the source. In other words, it produces an artificial zero. The source character won't have that zero, but with its ghost, there'll be a destructive interference, among other issues. In addition, and I'm sure everybody knows, it has a damaging effect on low frequency. Okay, if you can remove the ghost, and you'll see examples here, many examples, to the degree that you are effective in removing source and receiver ghosts, you'll see a boost in low frequency. And there's interest both within this group and outside this group on that, okay? For reasons that I alluded to. You understand? Yes. So you'll see lots of numerical and field data examples on that situation. So, for the purposes of deghosting, so the previous, what we did a minute ago, gives you under the cable, it predicts the reference wave above the cable. If you evaluate that, you get the portion of the total field due to the Earth only, which we call the scattered wave. So P0, PS in the previous application. We'll go back to that before we go into this, because it's important. Here we evaluated it below, and we got the field due to the source above. If we evaluated it above and closed it on top, we would have gotten the portion. This same integral will give you the portion of the total field when you evaluate it here due to this source. In other words, the portion due to the Earth and not to the reference medium. Clear? So why is that important besides wanting P0? Let's say you're in water that's where you have the reference wave and your reflection data, and they interfere. Often they'll cut. Well, you paid for that long offset data. This will predict the scattered wave. Everybody understands? It predicts it. You don't have to cut. It will predict at a point above the cable. So you say, well, maybe I don't want above the cable. Let's say I want on the cable. Well, that's what we know how to do now. Because we needed it for land. Everything has to happen at the cable. There's no predicted in the air. There's no water above to make another cable in your prediction. You understand? The land issue forced a lot of things, and frankly, there was some positive communication on issues like that with ExxonMobil colleagues on marine issues, which will we thank in one of our reports, pushing on some of these things. And their interest was marine deghosting. Okay? So, okay, so that integral, if you put G0 is G0D plus G0Fs, gives you, in other words, the reference is vacuum and water, and you evaluate that along the cable. You integrate that along the cable, evaluate it below, you get the reference wave, you evaluate it above, you get the scattered wave, meaning G0 plus times the source due to the earth. Okay? That's, just put that aside, you're going to see tests on that, okay? Examples with that. Now we're going to a separate, this is a different type of wave field separation. This is for the purpose of deghosting. The other was P0PS. Yes. This is separating up and down waves in your that arrive in your receiver or leave the source, and both. Okay. For that purpose, we pick a different reference. The reference is homogeneous, water everywhere. And then if water is everywhere, we have three things to add to make reality. One thing is we've got to put an air gun. The other is we got to change water above the free surface into air. That we will write as a source. Okay? A source term on the right-hand side of the differential equation. So there's three sources here. 1, 2, 3. Before there were two, because this was part of the reference. Okay? Before, not now. We have a different interest here. This work was pioneered by Jingfang Zhang in his thesis. He's at BP. Okay? This work we're about to show. So, because our reference is just homogeneous, you just have an out wave. Homogeneous from source to receiver, just the wave goes direct. That's what you see on the bottom. In 3D, just an outgoing spherical wave, frequency wave. So you have three sources, one due to the air, one due to the air guns, one due to the earth, each with an outgoing wave. So if you have your cable and you evaluate that integral with that G0, which is just an out wave, then let's say you evaluate it, well, first of all, if you evaluate it above the cable, you're getting the portion of the total field above the cable, in other words, in that volume, due to the earth. That's the only source outside this volume, yes? If I evaluate it above the cable. If in addition, I not only evaluate that integral above the cable, but I evaluate it above the cable, but below the source. That's very important. Above the cable, but below the source. Let's go back. Let's say I do that integral, I evaluate it above the cable. Let's say you have here's the water bottom, there's some cable here. And I evaluate, the volume is this and closed. I evaluate it at a point R here, but R is below the air guns and above the cable. The wave in that, with this kind of G0, leaves every source. It just goes out. So from the earth, it's going up at that point. The air gun response at this point here below is down. The air is down. So if the point that you evaluated is above the cable, but below the air gun, you have the only up wave at that point. You receive a deghosting. Okay? It's that simple. In other words, the other two are going down. In fact, what you've done there is you've gotten you removed what we would call a reference wave, and also you took the scattered wave and did receive a deghosting. Let me just repeat that. It's very simple. In other words, there are three sources here. Earth explodes, air gun explodes, and air explodes. And with that G0, they're all going away from their source. So the one from the earth is going up. If you did this, it's going away. From the air guns, it's going away. From the air, it's going away. At this point, this going away is down. This going away is down. This going away is up. So when I get the portion of the total field here, due to this source, it's up. And it's the only portion that's up. And hence, it's the deghosted part of that wave. Okay? So that leads to a very important expression. This is saying, we'll skip this. Okay, so it leads to a deghosting expression like that. In other words, what's the difference? This integral looks very similar to the one you had that's made P0 and PS. The only difference is the G0. If you make G0 the whole space just exploding Green's function, you get receiver deghosted that way. Okay? If you make it the reference Green's function for air and water, you get two pieces in your G0, and then you get P0 PS. So it's the same integral with two different G0s, and the code that's been delivered by Jim Mahan in 2D and 3D gives you both options. The same code, you put two G0s, different G0s in, and you apply it again, and you get source deghosting. Okay? And we'll go into, okay? So that's basically what's going on. So this sounds very esoteric from a traditional deghosting. It sounds, let's connect this up to what we're used to, okay, is the point, and show how this, in a special case, derives the simple up-down separation we're familiar with, and provides, and when one and the other provides value. Okay? This is not, this is in this formula for the deghosted field above the cable is, this integral is being evaluated in X omega. It's a single frequency theory here. Yes? It works shot by shot. It's what we call an X omega. In other words, nothing has gone to Kx. Whereas P is X at the cable, the source, omega, and so on. This is G0, its variables are R, the output point, R prime along the cable, and omega, integrating on R prime. So this is what we call an X omega form of Green's theorem, for the reasons I just mentioned, right? There's nothing that went to the Kx, the conjugate of X. That has advantages and disadvantages. This will, you cannot apply this for our interest to land. Okay? You gotta go to Kx omega. Kx omega has that advantage, it has other disadvantages. Depends on what you're after. That's what we're about to say, okay? To describe and illustrate. So, before you ever heard of George Green, what is deghosting? In some simple world, you can think of, you're in a homogeneous region around the cable, you just want to get the up wave that receiver had. Yes? So in some homogeneous region, and considering 1D normal instance, we'll generalize that in a second. You have a form A to the IKZ, B to the minus IKZ, and you want B. If you assume E to the minus I omega t is how you go from omega to t, then B e to the minus IKZ is the up wave, and the other A is the down wave. So what you want, simply, and you're never going to get away from it, it's very important to keep these things in mind, into these integrals and so on, okay? Because it's always boils down to this somehow. There are two ways, and this is a key point, there are two ways that come to mind to get A and B. One is you give me the value of P and its derivative at one depth. And you solve A and B, you get these formulas. And B is the guy you're after. Okay? Another way which is mathematically equivalent, is you give me the value of P at one level and the value of P at another level. Okay? And you get, those two will be absolutely the identical, okay? So, this is, you'll see, P in the derivative at one level. We'll derive from this, that, okay? To see the issues in the derivation. The issues in the derivation are all the reasons they have practical differences. The steps you take in the derivation. Clear? Okay. And why there are times when this is superior to the its Fourier form, and when the Fourier form is superior to that. Clear? So this is what I said a minute ago. Another way to get the A and B is to take the field at point 0, let's say the free surface. You would make it 0 if it was at the free surface, A plus B is 0. And it's, in other words, at two levels. And from the values of the field itself at two levels, you get A and B. Please remember this is critical in all what we're going to do, okay? Two ways to get A and B. One is at one level, get the field and its derivative. How do you get the derivative? We're going to be discussing that in detail, okay? How do you get in practice that derivative? And the consequences of that. But let's just stay with that. So you will get the exact same value for A and B with perfect conditions here. The difference is you have a denominator here, very different than you have here. That denominator is innocent. It's not going to be 0, 2ik. When you have at two levels, this sine Ka business, yes, it could have zeros. It could have zeros where the numerator doesn't, because you have the wrong depth. It's slightly off. So this can have a sensitivity. I'm talking about practical now. I'm saying perfect, this A and B, the other are the same. We understand two equations, two unknowns. Doesn't care where the two values come from. We're talking, there's some advantage of the other over this. And that was basically the theme of last year. In some fancied up way with old Green's theorem. There was that, be careful if you're around notches, for example, where the sine K is 0, that other slide is your preference. Okay? In notch area, that's, yes, a sensitive region for a division. If you're not in the region of a notch, in other words, if your notch is 125 hertz and you have 70 hertz of data, that issue might not be that important. Okay? Both on the receiver and the source side. Depends on where you are. If you're at the ocean bottom, very important. You're going to have a notch at 5 hertz. And then all things that other slide imply come in, including on the source side. There are similar derivatives with respect to source. In other words, this is like a double application of Green's theorem. You apply it on the receiver side, you do reciprocity, you do it on the source side. Just like Clayton Stone for migration. Double Green's theorem. One got the receiver down, the other got the source down. Same kind of idea. Okay, so we just said this, notches. Okay, this is saying the double Green's theorem. So this is the receiver deghost, you would do this, and then you will apply the same, and you're going to see Jim Mahan's work on this. So this is a robust method to source and receiver deghost. This would require over-under sources. Just like you have dual measurements on the receiver side, it would require dual sources. This is, there are ways that which I recommend you read Jingfang Zhang's thesis. If you're away from notches, this is overkill. Okay? There are things you can do, especially on the source side. If you get the wavelet and just the field along the cable, you can do source side deghosting effectively. Okay? You don't need that over on the sources. That's very important. If you're on the ocean bottom and your notch is in there, you better get over on the sources. For the stability is very important if your notch is so close into your data, yes? So it depends on where the notch is and where your acquisition is, how deep the source of the receivers, and so on. So, but this is sort of the gold-plated version. When you want to spend and you have and you don't want to worry about notches, that's what you do. If you are away from notches, please read Jim Parmesan's thesis and the work in Jim Main's thesis, which further develops that, of what you can do under different circumstances. Yes? With variants of Green's theorem. There you go. Jim Parmesan. Is that the end of this? So, you want to take a coffee break? Okay, once you take a coffee break, I'm going back to Houston. So, what, let me just tell you what's coming up. Depends on, maybe I shouldn't. You'll take a longer coffee break. What we're going to do is we're going to take that integral, that's that integral form of deghosting, and we're going to Fourier transform it and beat it into something that looks like a to the ikz and so on. The traditional, that's what they call PVZ, yes, summation. And we'll see what assumptions you make along the way, yes, towards that purpose. And then what are the limitations of the non-Fourier transform form? The downside of that, and I just wrote that integral, has a downside. And what are the downsides of the Fourier form? And they let you then know when you would apply one or the other. For example, when you do Fourier transform, you gotta be Fourier transform. If you have an ocean bottom like this, that surface integral has no problem. It never said anything about flat, just integrate. You could do you got the topography integrated. You do this on the surface measurements with different elevations, you're gonna have issues. That PVZ is not where to go for that. Okay? But there are other times that it is essential. So we want to give you a balanced view of that, and then also different acquisitions, and then a new way to deghost that we feel avoids some of the issues. If you just PVZ, one of our sponsors does that. They get, instead of the normal derivative of the pressure, you substitute it with the vertical component of particle velocity. And there are acquisition for arranging that. There are issues, as there are with all methods. The issue there is the VZ measurement doesn't go to low frequency well. There are instrument response differences when connecting different kinds of measurements. The over-under cable, if you're using over-under cable for getting a derivative, there are issues. You got a finite difference approximation to a derivative. Each is a downside. We're going to describe those differences and then propose a method that will avoid both of those downsides and show results. Okay. So that's basically what happened after the coffee break. Okay, we'll see you in a few minutes.